Guys, this is our second day of 1 minute speech. So today we are going to have the speaker, PLDI speaker for today and tomorrow morning. So one thing I can guarantee you is that we have plenty of coffee and cake outside. So please stay. So you don't need to rush out for a piece of cake. Okay? So now let's start it.
Hi everyone, I'm Jacob from UT Austin, and I'm here to convince you to come to our talk first thing this morning. And now, let me take you out of the matrix and introduce you to Morpheus, our tool for automating data wrangling tasks in R. On the right side, you can see the old world of doing data programming, where people spend 80% of their time doing tedious table transformation tasks. Scientists spend hours upon hours banging their head against the keyboard just to make their data readable. If you wish to stay in this old world, take the blue pill. Wake up in your bed and believe whatever you want to believe. However, this isn't the only world that's out there. What if I told you that such programs could be synthesized for you in only a matter of seconds? If you wish to see how these programs can be synthesized for you, take the red pill, leave the matrix, and come to our talk first thing this morning. Thanks.
Okay, so we live in a world now where computer networks are increasingly running more and more critical services. However, at the same time, every year there are major network outages caused by human misconfiguration that can create substantial disruptions in people's everyday lives. So for example, last year, Southwest had to ground 2,300 flights in the United States because a router failure caused a large part of their network to go down. So in my talk, I'm going to describe how we can use ideas from programming languages to try to address this problem of network configuration. And in particular, I'm going to talk about a new language and synthesis tool which can take as input a network-wide routing policy, an abstract topology, and a collection of fault tolerance requirements, and then from that synthesize low-level parameterized distributed configuration templates for off-the-shelf distributed routing protocols. And by using abstract networks, we can scale this type of configuration synthesis to large networks hundreds of times faster than existing tools, and also help incrementally deploy networks over time. Thank you.
So SQL is the de facto language for relational databases. But today, I'm not going to talk about SQL. I'm talking about how to synthesize SQL from input example to help with end-user SQL programming. Our algorithm breaks down the original expensive search process into two-phase search algorithm. We use the notion of over-approximation and big-variable encoding to scale up our algorithm. We're able to solve over 100 several SQL posts within several seconds. Come to our talk in synthesis track. Thanks.
So computers do all kinds of weird things to memory operations, like reordering them kind of crazily and surprisingly to make things go faster. And the rules by which they do this are called a memory consistency model. And it turns out that formalizing one of these models is a really Herculean task. So in my talk, I'll tell you how to synthesize automatically formal specifications of memory consistency from examples of the kinds of things a processor can do. And then I'll do one better. I'll also show you how to automatically disambiguate these synthesized models to discover ambiguities in the formal specifications themselves. So if you're interested in synthesis, you'll learn how we can synthesize formal specifications that themselves contain quantifiers. If you're interested in memory consistency, you'll learn how we can automatically synthesize a new kind of formal specification. And regardless of what you're interested in, I'll tell you why there's a cat on the slide. Hope to see you there.
Hi, I'm Paul Gazzillo. I'm going to be presenting decomposition instead of self-composition for proving the absence of timing channels. Software has secrets, and like passwords, and with side channels, an attacker can find these secrets indirectly by exploiting running time. So what we want is a static analysis where we can see whether these vulnerabilities exist or not. But this is a hard problem because we have to reason about multiple executions of the program at the same time. What we have is a reframing of this problem so that we can use a non-relational analysis that only has to reason about individual traces to prove whether an attack exists or not. So come to the talk. It's the first talk of the day in Aula Master. We have algorithms, cool security problems, and formalism, and a tool. See you there.
Hi everyone, I'm King Hipping, and I will tell you about automatic program inversion using symbolic transducers. We built a tool GENIC, which is based on the theory of symbolic transducer and syntax guide synthesis. GENIC can invert programs such as string encoders and decoders for encoding schemes, base64 and UTF. My talk is in the next section, and please come to my talk if you want to know how GENIC works. Thank you.
Hi, I'm Peter, and I'm here to tell you, sadly, your application has crashed. And worse, it's crashed in production. So you probably have a lot of questions about what happened. Come see our talk in the next section, where I'll talk about how we answer user questions over failure reports using ideas from symbolic visibly pushdown automata and subregular languages. We answer questions via automata intersection emptiness. We're able to answer these questions over programs up to 200,000 lines and failure reports with 13,000 elements. If you want to hear more, stop by in the first section.
All right. Cache attacks are able to break crypt implementations by exploiting differences in the execution time that are due to the use of the CPU cache. And multiple such attacks have been shown in all the top security conferences recently. So some widely used countermeasures have relied on techniques such as, for example, storing data in some special layout to ensure that when we are doing secret-dependent data accesses, the same sequence of cache lines is being accessed. Or making sure that secret-dependent control flow is small enough that it all fits into a single cache line. All right, so the security of such code can be quite brittle, depends on some details such as the hardware architecture and the compiler. So how can we establish the security of such countermeasures? Come to my talk at 12:05 in Ola Master and I'll show you how.
Hi, I'm Victor, and I'm going to talk about how can we synthesize parallel programs from sequential implementation, so a loop with dependencies, and if we just divide the loop, how can we find the merge or join operation to recompute the total result from the partial results? And if this join doesn't exist, how can we automatically find an extension of the loop so we can actually parallelize this loop? So please come to my talk today, this afternoon, first talk on parallelization and concurrency.
It is a commonly held belief that functional languages, while expressive and safe, are inherently slow. Well, they don't have to be. We've constructed Futag, a purely functional parallel array language that has been carefully designed to enable the creation of an aggressively optimizing compiler that can generate GPU code. Using the high-level invariants provided by a functional language, the compiler can do aggressive rewrites like turning nested parallelism into efficient flat parallelism. On a set of a dozen benchmarks, the compiler can generate code that is competitive with hand-written GPU code. So come to my talk and see how that works out.
Okay, parallelization of software is important for improving its productivity. I will present GRASP as an automated synthesis procedure to generate this parallel code based on the sequential implementation. GRASP considers 3 parallelization scenarios, and it walks through it gradually because it wants to deliver the simple solution as soon as possible. Importantly, GRASP has a certification to make sure that the solution is good for any input. Our experimentation, both on the laptop and at the Hadoop, shows the great performance. Go for more details from our talk.
Hi, I'm Colin, and I'm going to talk in the concurrency and parallelism session this afternoon about verifying invariance of log-free data structures, because they're still hard to get right. And we have a lot of new tools over the past few years for verifying them. But for many of those, they're no longer compatible with unverified code. You either need to pay performance overhead or just drop them in and hope for the best. So I'm going to talk about a way to enforce invariance, 1- and 2-state invariance that control mutation. in a way that's compatible with unverified code and has correspondingly intermediate proof burden, something in between what you'd get from a basic type system or a full-blown program logic. So if you want to hear about how this works in a lightweight Coq DSL or a liquid Haskell library, or if you want to hear about cool data structures like a lock-free Undefined implementation, come to my talk this afternoon.
In 1992, Andrew Appel, who was sitting there before he went to get cake, wrote this amazing book, TLDR. It said, if you're building a compiler, you should use continuation parsing style as your intermediate language.
We can keep it off and hopefully just turn it on when... Yes.
So I had a bit of inferiority complex about this because GHC, my compiler for Haskell, used direct style. So it was really good when Andrew Cormac Flanagan, who was also sitting here, wrote a paper that said, no, you don't need that CPS stuff. But then it turned out that Andrew Kennedy, my colleague, wrote a paper that said, yes, you do after all. So this paper is the knockout punch in that little interchange in which I show how you can use a direct style compiler, but still by adding join points, get all the joy of continuation parsing style in an intermediate representation without the pain of turning your life inside out to use CPS. Two o'clock, right after lunch.
It's a hard act to follow. So this talk is actually related. It's about mixing high-level and low-level languages. And you might be interested in this if you're interested in verifying just-in-time compilers, because if you think about what a JIT does, is it takes some high-level program and then replaces parts of it with low-level code. And so if you want to know that that's correct, you need to know that the original program is equivalent to that mixed resulting program. And this is challenging because the control flow between high-level code and low-level code is very different. You end up with continuation style on the low level and direct style on the high level. And so what we show in this paper is how you can mix high-level code with low-level code. It's a high-level functional language and a typed assembly language in such a way that you can ensure safety and also prove equivalence. Thanks.
Hi, so SQL is a language that is virtually supported by all relational database systems. Yet, trying to come up with a semantics for the language such that it can be easily used in mechanized proofs turns out to be difficult. So in this work, we propose a new semantics for SQL that is based on homotopy type theory, or HOT for short. Using this new semantics, we have implemented this semantics called HOT SQL on top of the HOT library and also using the Coq proof assistant. And we have used it to prove a number of new SQL equivalences that arise from the real world and haven't been actually proven correct before, using only a few tens of lines of Coq code. So if you want to learn more about why HOT is so hot, or simply try to understand how we transform type theory into reasoning about relations, come to my talk this afternoon and I'll tell you more. Thank you.
Hi, everyone. This afternoon, I'm going to talk a little bit about Levity Polymorphism. So in that talk, we're going to consider the tension between the beautiful structure of polymorphism and the raw power of performance in coming up with a new way to write polymorphic code that is performant and convenient to write. So this is through a new form of quantification, essentially quantifying over a calling convention. But it turns out we can't always do this, so you'll see this afternoon why we can't. And yet using this technique, we can generalize almost half of the standard library in GHC's standard library distributed with Haskell. So come to the talk this afternoon at 3:15.
Hello, everyone. I'm Ori. I'll speak afternoon about this paper, Repairing Sequential Consistency in C++11. And we all think, I guess, that sequentially consistent memory accesses are simple. Well, this is not the case in weak memory settings when you have multiple accesses of different sorts to the same location. And in fact, we found out that the C++11 SC accesses are broken in the sense that there are programs for which if you compile the program and run on hardware, you might get behaviors that are not allowed by the specification. In the talk this afternoon, I'll show what exactly went wrong and how we propose to fix it. Thanks.
Hello, in my talk this afternoon, I'm going to talk about the problem with undefined behavior in LLVM and introduce our semantics, introduce our new solution to the problem. So, I'm sorry. There are many miscompilation errors in LLVM, and also we reported the miscompilation error to the LLVM, but currently there's no way for LLVM to fix it. So yeah, we suppose a new undefined behavior semantics which is simpler and also fixes the previous inconsistency. Thank you.
My name is Timothy Buck. What you see there is a screenshot from the ANSYS SRL Technology SCADE tool, which is routinely used to program safety-critical software, like the fly-by-wire controller in Airbus A340, which you can see on that slide. Underneath SCADE, there's an academic language called Lustre. What we did was implement a compiler for Lustre. Basically, you put your data flow programs in one end of the pipeline, and it goes through all of those pipes, and then we've integrated the CompCert C compiler, which produces assembly code for x86, PowerPC, or ARM. What's special about our compiler is that we specified it and proved it correct in the Coq Proof Assistant. So please come this afternoon if you would like to hear more about Lustre, its compilation, and the proof. I promise there will be more source code than Greek. Thank you.
Hey, well, I guess a lot of us here may know about SAT or SMT solver, but today I'm not going to talk about that. Today I'm going to tell you about another kind of solver. It is about string solver. And our string solver can be built on the top of SMT solver. And what are new things about our string solver? So in our work, we propose a new framework for string solver. And our string solver is able to handle a rich class of string constraints, for example, context-free grammar and transducer and so on. And our work based on SIGA. It is a counterexample guided abstract refinement. Another thing about our work is we have a tool based on the framework, and our tool performs better than state-of-the-art. If you want to know more about our solver, so come to my talk this afternoon at 4:30. Thank you.
Want to implement a new programming language that's as fast as today's Java and JavaScript? You can either hire a dozen compiler and GC experts, or you can use our framework. We know since 1971 that partial evaluation of an interpreter gives you compiled code, but in the talk tomorrow, we'll show you how it's practical and feasible today. And as a bonus, you also get debugger and a profiler for free. And if you want an in-depth look, come to our tutorial on the Graal compiler Friday morning. Thank you.
Hi, I'm Stefan Muller, and I want to tell you about a separation that exists in the design space of threaded programs. On the one hand, we have competitive threading models like p-threads that try to gain the maximum responsiveness in interactive systems. On the other hand, we have cooperative threading models, as exist in some languages for high-performance computing, which try to maximize throughput in large computations. These languages have high-level abstractions for parallelism and elegant, provable cost bounds, but they have no way of reasoning about responsiveness or even interaction. And we believe this makes the models incomplete if you can't reason about the interactive programs that people use every day. So come to my talk tomorrow morning, where we'll begin to tear down this wall. I'll provide a cost model that allows programmers to reason about both the throughput and the responsiveness of parallel interactive programs, a modal type system that guarantees responsiveness in interactive programs, an implementation, and a bunch of cool benchmarks. Here's the title slide again, and hope to see you tomorrow morning.
Hello, I'm Konstantinos Mamouras, and my talk is going to be about stream query, a language for modular specification and efficient evaluation of quantitative queries over streaming data. In particular, we propose a language with a small and expressive set of core abstractions that combines regular expressions, quantitative aggregation, streaming composition, and relational features such as key-based partitioning. Our language has a formal mathematical semantics in terms of partial functions on stream histories, We also show that a high-level query can be compiled into an efficient streaming algorithm with precise guarantees on space footprint and processing time per element. And the good performance of stream query has also been validated experimentally by comparison with other popular streaming engines on practical workloads. So if you want to hear more about this work, please come tomorrow morning to my talk. Thank you.
Okay, thank you. So that's the end of the 1-minute speech. So the current session starts now, and the PLDI panel session starts from 10:50. And we have coffee and cakes outside.